hypothesis tests, these are the things that you want to carry out to prove a result statistically. And if you were at the session last week, you may remember we looked at a data set where measurements were taken on newborn calves, and there were 15 cases that had a particular quite serious disease and 173 normal calves. And this was a measurement here, I've summarised a white blood cell count, so you can see the cases have got much lower white blood cell count than the normal calves. And you might think that's enough, but you can go on to actually prove that that difference is statistically significant. So that's when you want to use a hypothesis test. So yeah, that's what we want to do, confirm it. And we want to be sure if we were to do the study again and measure white blood cell counts in a new set of calves, that we would still get a difference between the cases and controls. It wouldn't be exactly these values, but we would want to be sure that it was reproducible, and that's what doing a statistical test will tell us. So a hypothesis test, i.e. a statistical test, will give us some certainty about whether the groups, the cases and the normals, genuinely differ, or whether that difference is due to chance. So that's what our hypothesis test is going to tell us. Yeah, I think it's helpful to think about what a hypothesis test is, and we can think about this in stages. So the way you set out is you set what's known as a null hypothesis, and in our case it would be, well, white blood cell count is exactly the same for the cases and the controls, and this was just a chance result, getting mean values that were so different from each other. And what we do in our statistical test is we determine whether that null hypothesis can be disproved. And so the next thing we want to do is calculate a test statistic, and we're going to calculate that from the difference in the means and take into account how variable those means are, and come on to this in a bit more detail a bit further on. But a common test statistic for comparing two means is known as a t-statistic, and that's simply the difference in the means, one minus the other, divided by the standard error of that difference. So if you remember, the standard error is a measure of accuracy, and we want to get the standard error of the difference. And without going into the calculation, if we do that, we get this number, which is our statistic. But what does that mean? What we want to think about is, what would we expect the distribution of this t-statistic would be if under the null hypothesis. So we'd expect it to be 0 under the null hypothesis with a range of values about it. The expected distribution would look something a bit like this, and we'd expect the value to be 0, but there'd be a certain amount of variability below and above 0 expected by chance. And you might not be able to see this properly, but basically values of about -2 and +2 are reasonably uncommon. When you get to -3 and +3, they're very uncommon. And so you can see our value here, 16.21, is really unlikely given this distribution of our null hypothesis, and it would be somewhere way off the scale. And that would lead to a very small probability of the null hypothesis being true. And that's what gives us our p-value. So the p-value is defined as the probability that the null hypothesis is true given our test statistic. So the probability under this distribution that we get a value of 16.21. So hopefully you'll be able to see that this value is really unlikely given that distribution. And sure enough, we can, from that distribution, get the p-value. The p-value is very, very small and less than 0.0001. So because the p-value is very small, that allows us to reject the null hypothesis and conclude an alternative, and that is that white blood cell count differs between the cases and controls. So what we can say is we've got a statistically significant difference between the cases and controls. And we can report that in our paper or wherever we're reporting the result. So that's the mechanics of how a test works when you're comparing two groups. And it's this p-value that's the key thing that you're after, the probability that there's no difference in the groups. P-values relate to statistical significance. As I've said, it's a probability that that null hypothesis is true. In our case, that white blood cell count was the same for the cases and the normal calves. Convention, and there's no real reason for this, but the convention is to say if your p-value is less than 0.05, then you've got a statistically significant result. Sometimes that's called the 5% p-value, and you should be able to see, but what that equates to is that there's only a 1 in 20 chance that the null hypothesis is true, and that's kind of deemed as kind of good enough. You know, if 19 out of 20 times, then you're correct in concluding, in our case, that white blood cell count is higher in the normal calves than the cases, then that's enough to conclude that they're statistically and significantly different. Of course, the lower the p-value is, the more certain you're going to be about that. Smaller p, greater certainty that the null hypothesis is false. For example, we had p, in fact it was less than 0.0001 for our test, and that gives us a lot of certainty that there is in fact a difference in white blood cell count between the two groups of calves. And another way we could describe that is we've got a highly significant result, so we're very sure about it. One thing to be a bit wary of is quite often you're going to have p-values that are not significant, and it's quite often tempting to say, well, there's no difference in my groups, but sometimes that's not true. It might be just that you haven't got enough data to show there's a difference. So if you get a non-significant p-value, what you're really concluding is you haven't proved a null hypothesis and you haven't got enough evidence to reject that null hypothesis. I mean, it does give you some indication that the groups might be the same, but you can't ever conclude the groups are the same. All you can conclude is you haven't proved that they're statistically different. You want to do a statistical test, but there are a whole range of different tests available, and they all have quite obscure names that you just have to get used to. But it does depend on the type of data you've got, your choice of tests. There's different tests for continuous data, like something like height or counts, compared to binary or categorical data. So there's tests that fit different circumstances. Some of the tests depend on the data structure. For example, well, in our case, where we looked, we just had 2 independent groups. There might be 3 or more groups, and a t-test, well, the test that we just looked at isn't appropriate for that, and there are other tests that can be used. There might be more complex structure to the data than just simple groups. The calves, for example, may have been grouped into farms. There may have been your experiment may be repeated several times and you want to put all the data together. So you might be in a situation where there's some structure, and that has a bearing on what sort of test you're going to do as well.